All right, let's get started with number 5 from the midterm. So if we look at the for loop, we can see that it'll go into I is less than 2 times n. And then I plus equals 1. So I increments by 1. So that sort of indicates that we're going to have a 2n runtime, but the directions say to knock off extra coefficients. So we're going to settle with n. And that's a classic for loop example of runtime. So if we look at the second problem, let's zoom in a little. Okay, so we can see that we have 2 recursive calls, one right there, and then one at the bottom. Yes, and then we call f of 1, which we just found out has a runtime of n. Okay, so let's branch and see what our recursive tree will look like. So if n equals 8, we'll have 2 calls to n equals 4, because we're going to divide 8 by 4, or by 2 twice and get 4. And then we're going to do that again with the 4, get 2 2's. So as you can tell, this is resembling a log n runtime. So if you finish the branch, okay, great. We can see how each set of the branch is one of the recursive calls, and it just iterates down through. So looking at that, we get n log n, because the n from calling f1 and then log n based on the recursive calls we have right here. So if we take a look at the next part now, we can see that we have 3 recursive calls, but this time we're dividing n by 3 in each call. And then we have 2 calls to f1. So I'm going to go ahead and draw the recursive stack, assuming n equals 9. So for each, I guess, recursive iteration, you're going to have 3 branches, as you can see here, until you hit your base case, at which point you return. And so with each of these iterations, or each of these recursive calls, you're going to have 2 runtime of n functions in there, which are the f of 1 runtimes. So you're going to get a total of 2n log base 3n. So log base 3n comes from that tree that you can see above based on the 3 recursive calls, and the 2n comes from the 2 calls from f of 1. And so again, if we simplify, we'll knock off the 2, but we'll keep the n, and so we'll get an n log n runtime. Okay, so if we look at the next example, F4 here, we'll see that we also have 2 recursive calls, and so I'm going to write them out like an equation. So fn minus 1 plus fn minus 1 plus f of 17, which is going to be constant time because it's in terms of 17, not n. So we simplify that to 2 fn minus 1, and then we'll just take that out, put it as 1. And we can just cancel it out completely because we don't need the extra things that you add up and the coefficients, because we want the simplest version of our equation. So then if we go to the next recursive call, we'll carry our 2fn minus 1, and then we'll go ahead and do 2 times fn minus 2 plus the 17 from the f of 1 call. And then we're going to toss out the 17 again like we did last time because it's not significant to our overall runtime here. So here we can start to see a pattern. If we have, well, let's go ahead and simplify this first. Okay, well, the first part of the equation on the left-hand side is essentially 2 times 2 to the n minus 1. And the right-hand side will be 2 times 2 to the n minus 2. And the way we got that was that each of these recursive calls are going to have 2 branches. So a similar example, if you want to relate this to something, would be Fibonacci, that also has a runtime of 2 to the n. It's the fact that we're having 2 recursive calls of about the same size. Earlier we were dividing by a number, but now we're only subtracting 1 at a time, which is not a very significant amount. So I'll go ahead and draw out the recursive branching. right here. And so the n is 5, and so with each call we're going to subtract 1. And so on. It'll go down to the 1s. So if we look at the number of levels we have here, you'll see we have 5 levels, which is the same, equal to n, our original n. So we'll have 2 to the n, which also means 2 to the 5 in this case. So we'll have 2 to the 5 recursive calls, recursive branches, I guess, as you'll see here. So in our branching, you can see how that kind of relates in that example. So if you're still feeling a little bit shaky as to why this is 2 to the n, you might want to reflect on the Fibonacci example, which might give you some more clarity. So on to the final part of the problem. We can look at F5 and we'll see there's a for loop and a recursive call. So in the for loop, we're going to iterate through n times. So there will be n iterations. And then inside of the for loop, we'll have m recursive calls for each iteration. Alright, so for each m minus 1 recursive calls, sorry, I meant to write recursive calls, you get n loops. So it'll loop n times per call, right, according to the for loop. So therefore, I'd argue that the runtime here would be n to the power of n. Alright, so let's walk through an example. So let's say n equals 3 and m equals 4. So I'm going to go ahead and write all the recursive calls that would happen. So this is for the I equals 0th iteration. So we would have f of 5, 3, 4, 3, 3, 3, 2, 3, 1, and then 3, 0, which would be our base case. At this point, I will increment by 1, and we'll again repeat the exact same process. So it'll again be 3, 4, 3, 2, 3, 1, and then 3, 0, you hit our base case, and then I again will increment by 1. So I here, our counter, is represented by n, and then we'll have m iterations per n. So then we can conclude that we will get n to the m runtime. But the key here is that each of these recursive calls I've listed for each iteration, they're each going to have recursive calls of their own. That's why we put n to the power of m.